everyone. Thank you all for joining us today for another webinar hosted by Hamamatsu. My name is Emily Bottomiller, and I am the Industry Program Manager with SPIE, and it is my pleasure to be your moderator this afternoon. This is the third webinar in our series of 6, and if you missed the previous 2 webinars, you can view a video recording of them on the registration landing page. As we get settled, feel free to introduce yourself in the chat. I see many of you have already. And our presenter today is Slawomir Piatek. Slawomir earned his PhD in physics at Rutgers University and is currently a science consultant at Hamamatsu. He's also a physics professor at the New Jersey Institute of Technology. At the university, he has been measuring the proper motions of nearby galaxies using images obtained by the Hubble Space Telescope. And at Hamamatsu, he has developed a photonics training program for engineers. How great. And now I'll pass things off to him. Welcome.
Okay, go ahead. Eliminate. Okay, thank you, Emily. Now we are finally set to proceed. So first of all, I would like to thank everyone for signing and listening to this 1 hour long webinar. As Emily said, we are going to be discussing plasma-based light sources. Actually, we are going to concentrate on a single but truly innovative light source. The presentation is divided into 3 parts. In the first part, I will briefly review some of existing light sources. This review is primarily for future comparison between these sources and the laser-driven light source, which will be the main topic of today's webinar. In the third part, again, briefly, I'm going to discuss some possible applications of this laser-driven light source, or LDLS for short. So let's review some of the existing light sources. Let's begin with the Blackbody. This is a thermal source, which means that the light emitted is due to heat that is provided into an object. This source emits light with a well-known spectrum known as Planck's body or Planck spectrum or broadband spectrum, described by the function above the plot. The total power emitted by the source is a function of basically 2 parameters. One is the temperature to the 4th power. So the emitted power is very sensitive to temperature and also depends on the size of the emitting region. Please note that the spectral shape is only dependent on the temperature, and the peak emission occurs at lambda max given by Wien's law. There are a number of Blackbody sources realized in practice. And here we see an example of a source, a quartz tungsten halogen lamp. These sources are used in a variety of applications, for example, as microscope illuminators or just general illumination. Not long ago, every household had incandescent light bulb, which was effectively a Blackbody source. Before moving on, I would like to point out some aspects of these sources. One is that modulation is rather difficult. To modulate the emitted power, one would have to change temperature of this or size, and that's difficult. And so to do modulation, external modulators are going to be used, choppers, for example, or some other devices. Another point I would like to make is that to increase the power, I could increase temperature, but that will change the spectrum. So if I want spectrum to be fixed, I would have to increase the size of the emitting region. Let's now go to the next class of sources, discharge tubes. So these are plasma sources. The basic design is as follows. We have a glass bulb and 2 electrodes connected to a current or voltage source. One ignites the plasma region by applying appropriate amount of voltage or current. The plasma is then maintained electrically. So the electrons flowing between the electrodes via collisions with the atoms in the gas, keep the plasma quote unquote alive. The basic mechanism of light production is shown with this energy diagram. So through collisions with electrons or with other atoms, the atoms can get excited or ionized. Once excited or ionized, then electrons are going to go back to the lower energy states. So now we are going to have a spectrum that is a combination of bound transitions. These are going to give us distinct spectral features. And then there will be a broad continuum. And this continuum is due to continuum to bound state transitions. Please note that the form of the spectrum or the shape of the spectrum is highly dependent on the property of the plasma, i.e. its temperature and density. And that will be determined by, again, the amount of current that passes through the plasma. The variety of gases used for these discharge tubes. And here we have a graph known as Paschen's law that tell us what voltage must be used as a function of pressure times distance relationship for the different gases. So from this plot, what we see is that the voltage needed depends certainly on the pressure of the gas, which means effectively density, but also depends on the distance between the electrodes. What this plot does not tell us immediately, but it is true that also the voltage will depend on the shape of the electrodes, since the shape of the electrodes determines the shape of the electric field between them. Here is a little table that shows some commercially available plasma discharge lamps. This is certainly a small sampling. So we have deuterium lamp, xenon flash, xenon lamp. So these lamps can operate in a continuous mode, which means DC light, or as flash. So here is the xenon flash representing that region. There are some important considerations when one thinks about the light sources. One is certainly the wavelength range, stability. The stability means how stable the light output is. Does it fluctuate? Does it fluctuate on a small time scale, long time scale, etc.? Lifetime, how long the source can operate effectively, and some features and applications for these particular sources. So before moving on, I would like to say a few things about these sources. So again, the spectrum range will depend on the type of gas that is used. These light sources do have finite lifetime that is measured in only thousands of hours or some number of flashes in case of the xenon flashlight. And so we're going to discuss now why there is a finite lifetime. So please note that when I look at the plasma region, the plasma region is going to extend effectively from one electrode to another. This gas is here hot and ionized. As a result of that, the electrodes are going to corrode, and also there will be a spattering taking place. So in case of spattering, simply the atoms from the electrode are going to liberate themselves and eventually settle on the inner part of the glass tube. There may be a reaction between the metal of the electrode and the gas, and that is going to lead to corrosion. So the spattering will effectively be responsible for dimming of the glass enclosure, and the corrosion will affect the shape of and intensity of the electric field. As a result, the plasma region or the arc may change location. If it does, we call that flickering. So darkening and flickering flickering will effectively limit the lifetime of these sources. Let's now go to solid state sources, beginning with light emitting diode. In case of light emitting diode, we have we have a semiconductor P-type and N-type. This type of semiconductor is known as a direct bandgap semiconductor. If I create a PN junction and I forward bias this PN junction, current is going to flow. In certain region, there will be recombination between holes and electrons. Because this is a direct band semiconductor, this recombination is going to lead to emission of light. And so that's our ordinary well-known LED, light emitting diode. The spectrum will depend on the type of the semiconductor. So using different types of semiconductor, I can get different colors of light emanating from this structure. The spectrum is rather narrow. So to obtain so-called white light, one can do a trick, have, for example, light from 3 LEDs, one emitting in red, other in green, and the third one in blue. This does not produce true white light, but to our eyes, the light would indeed look whitish. To have a more broadband emission from LED, one could do coating with phosphor material. And so that will change the spectrum emitted from the LED by the presence of the phosphor coat. Another interesting solid state light source is supercontinuum. So what we have here is high power femtosecond laser producing high power pulses with high repetition rate. These pulses propagate through a nonlinear optical fiber. As the pulses propagate, they are going to broaden in spectrum and in time domain. And so the spectrum N can be a narrow line. Known lasers produce such narrow emission. And as a result, we have a wider spectrum. At the bottom of the slide, we see an actual spectrum obtained with 820 nanometer titanium sapphire laser. We can see the broad distribution from about 400 to about 1,400 nanometers. So effectively here, monochromatic light has become a broadband light. What kind of spectrum you get will depend on the fiber that one uses, but also on the pump laser. So this is a neat plot that shows basically spectral density. You can think of this as a measure of brightness as a function of wavelength for different pump lasers. We can see that this technique can give us emission deep into infrared. However, please note that there is not much light emitted in the ultraviolet part. Another class of light sources are lasers. Here we see basically the first type of laser developed, which is a helium neon gas laser. All lasers have the following features in common. So one, need to have some resonant cavity. Second, you have to have mirrors at the end of this cavity. One mirror is going to be nearly perfectly reflecting, whereas other will be somewhat transmitting. Another feature is that you need to have inverted population of atoms or electrons, and a technique to keep that inverted population. So there has to be some pumping technique. There are various ways of pumping. In this particular laser, the pumping is facilitated by collisions. So once in excited state, then electrons are going to transition towards lower states emitting light. This emitted light is going to stimulate emission in other neon atoms. So effectively, the light produced is due to stimulated emission. This produces highly coherent and non-divergent light. It's actually not completely non-divergent, but it certainly has smaller divergence than in case of, say, Blackbody. Of course, for emission to continue, we have to keep pumping, keep the inverted population. Another realization of a laser is a diode laser, very popular, common, very easy to use. This looks like a PN junction, but it's not exactly LED because, like every laser, it has a resonant cavity with the mirrors at the end. Here, the inverted population is produced by forward biasing. Once we have enough forward current, we reach the inverted condition where stimulated emission is going to be sustained. Another device that I'd like to mention is superluminescent diode. This diode is kind of like a cross between LED and diode laser. So on the left-hand side, we see power as a function of current. For LED, this relationship is linear. For diode laser, it's nonlinear. In case of SLD, it's somewhat in between. A more maybe telling plot is the spectrum intensity as a function of wavelength. And so here we see the clear difference between LED, SLD, and DL. So diode laser is going to produce a narrower spectrum, as lasers do. LED has somewhat broader spectrum, and SLD, superluminescent diode, has a spectrum that is sort of in between the two. To quickly finish this section, I would like to mention some other designs of diode lasers. This is the famous Vixel. It's basically a PN structure, a more complex PN structure, but the emission here is perpendicular to the layered structure. So they are vertically emitting lasers. One great advantage of these sources is that you can have many, many points where light is being emitted. So you have a sheet, you could have a sheet of emission of light. And finally, another interesting light source is quantum cascade laser. Here, we create a lattice, sort of layers of materials which create quantum wells. By appropriate biasing, the quantum wells can be tilted in energy, and electrons will cascade from higher energy to lower emitting photons. This quantum cascade laser is very important, for example, in gas analysis, because it produces tunable infrared radiation. So with this, let's now move on to the second part, where we are going to discuss another type of perhaps less familiar to the audience light source, laser-driven light source. I'll begin with a basic picture, and then we are going to discuss in greater depth the physics and eventually possible applications of this source. So there are basically two important components to this source. One is the bulb with electrodes. So this looks like a discharge tube that we discussed a few slides ago. In that bulb, we have a high pressure gas, most commonly xenon. The second important component is a laser, continuous wave, typically in infrared and high power. The power of the laser can range from 20 to 5 kilowatts. So very briefly, what happens? So in the first stage, we are going to ignite a plasma region electrically. So a voltage is going to be applied to the electrons where a small plasma region forms between the electrodes. And then light comes in from the laser. The light is focused in such a way that there is high enough density of photons in this region to maintain the plasma. So the plasma is maintained by light from the laser. This plasma region emits light. So effectively, we have light produced by light. However, please note that the light coming in is monochromatic because it's a laser. However, the light that will come out will be broadband with some characteristics that are of great practical usefulness in some applications. Before moving on, I just wanted to note that this region is very hot. The temperature in this plasma region will vary anywhere from 10 to 20,000 degrees Kelvin, which is hotter than the surface of the sun. So let's now look at the physics details of this lamp. So as we said earlier, the first step is to ignite the plasma. Of course, the laser can be on already, but we did not put it in the picture, so we don't clutter the slide with necessary information. So the high voltage ignites the plasma. The working gas typically is xenon, and so please note that ionization energy of xenon is actually quite high, about 12 or so electron volts. Now we have light from the laser. So the light is focused on the plasma region. The density of photons has to be high enough to maintain the plasma. In the next slide, we'll discuss the various mechanisms that transferred energy from laser to plasma. But first, this plasma region will consist of the following components. So there will be some neutral xenon atoms. There will be excited xenon atoms. There will be ionized xenon atoms. In addition, we are going to have excitation photons. So these are the photons that come from the laser. And then we have emission photons. These are the photons that were produced by the plasma. There is no plasma here, so here the gas is neutral, and that's because there is not enough density of excitation photons to maintain the plasma there. Even if the plasma was there originally, it's not going to be there if the density of photons is not high enough. A little bit of thermodynamics. The gas in the plasma is going to be hotter than the gas outside. However, the pressure in the plasma will be the same as the pressure outside. If pressures were different, then you would have quite a bit of convection or stirring of the gas. The density of the gas will also be different. So the density in the plasma will be less than a density outside. So how large is this light emitting region? Quite small. So on the right-hand side, we see an image of the plasma region, and we see that it's about 60 by 150 micrometers. I should also point out that the way we illuminate this plasma region is such that the light goes against the gravity. So if the laser light comes from the left, then G would be pointing in the opposite direction. There are practical reasons for that, but maybe somewhat beyond the scope of our presentation. So how does pumping occur? How do we transfer energy from the laser to the gas? So the variety of processes, please note that these processes are highly temperature dependent, so their importance may vary depending on the laser power. However, we are going to have non-radiative transitions. These will be due to collisions. These collisions can excite the gas to some metastable states. Furthermore, you could have non-radiative transitions due to collisions from metastable states to free state, which means into the continuum. If you're wondering why not go from ground state to free state by collisions, remember the ionization energy is quite high, and so the atoms simply do not have enough kinetic energy to achieve that one-step excitation to free state. Then we can have absorption of light. So we could be in metastable state and absorb laser light, and that will put you into free or ionized state. And finally, and probably most importantly, once we have electron in a free state, unbound state, then this electron can absorb light by so-called inverse Bremsstrahlung. This is most likely the most dominant mode of energy transfer from laser to plasma. Let's look at inverse Bremsstrahlung. If I simply had electron and a photon, this electron could not absorb the photon completely, because to do so, you have to satisfy laws of conservation of energy and momentum. And we cannot do that for full absorption. Yes, there could be some scattering, competent scattering, but not full absorption. However, if the electron is in the presence of a positive ion, heavy ion, this becomes a three-body interaction where full absorption of radiation becomes possible. And again, it's very effective in heating or maintaining the temperature of the plasma. Okay, so this was pumping. So light goes from laser to plasma. So now we want light from plasma. So these are the various modes of light generation. Thus, you could have free to bound transition, where electron goes from the free state, ionized state, to an atom. It's bound in some excited state, or maybe even all the way to ground state. Please note that the energy of the photon emitted here will depend on the initial energy in the free state, which could be anything, as a matter of fact, and the final energy of the bound state. You could get bound to bound transitions. These transitions will give you characteristic emission features in the spectrum and characteristic of the gas that is being used in this source. In our case, it would be xenon. And finally, you could have a free transitions. So this is a Bremsstrahlung, where electron does not bound to an atom, but effectively slows down. And so to conserve energy, energy has to be emitted. And that's the well-known Bremsstrahlung. So there has to be equilibrium, which means energy in must equal to energy out. And this will be the state, operating state of our light source. If you have more energy coming in than out, the plasma is going to respond in such a way that equilibrium will be reached. So now let's look at some spectra. So the top three curves are spectra for laser-driven light sources. These devices are labeled EQ. EQ stands for energetic, which is Hamamatsu's subsidiary, which makes these light sources. So let's compare these laser-driven light sources with some of the sources that we've discussed in the earlier part of the presentation. So here is 75-watt xenon lamp. This is a 30-watt deuterium. This is a Blackbody source, a tungsten. And so we can see that the laser-driven light sources have much higher brightness. So for almost, in fact, for every wavelength in this case, the brightness is higher from these sources. The spectrum also extends from the ultraviolet part to infrared. In fact, it will go even deeper in infrared once we see another spectrum shown here. So this spectrum only shows the EQ sources, energetic sources. And we see that the spectrum extends from, as we already mentioned, ultraviolet part to about 2000 or so nanometers. So quite deep in infrared. The spectrum, the shape of the spectrum kind of looks like Blackbody, sort of. except you do have these wiggles, spectral wiggles. And again, these will be due to the bound-bound transitions and mostly bound-bound transitions in the gas. So let's discuss some properties of the light from this laser-driven light source. As we saw on the previous slides, the spectrum is broadband. So if you are looking at the light physically, it would appear to you as white light. However, as we already mentioned, the spectral range extends from UV to IR. And so we can extract, and we'll see how that can be done, various parts of that spectrum for some applications. Now, the source has very high spatial coherence. And the reason for that, or the spatial coherence, is primarily affected by the size of the light emitting region. The size in this case is very small, just tens of micrometers. So that gives the source high spatial coherence. In practice, I don't have a slide showing that explicitly. We have lenses and mirrors that collect the light from the plasma region, and then the light is put outside via optical fiber. The light has low temporal coherence. And the reason for that is because this is a broadband source. Remember that laser light would have very high temporal coherence. More monochromatic light is, higher its temporal coherence. So since we have nearly black body type of emission, then that will be characterized by low temporal coherence. This aspect is useful in some applications, like, for example, optical coherence tomography. High brightness, we'll see shortly that only one source can compete with the amount of light produced, and that will be the super continuum. The light source is DC. Unfortunately, it's rather difficult to modulate the light or pulse the light because modulation or pulsing would lead to changes in the properties of the plasma. So ideally, one would use this source for DC applications. However, if pulsing or modulating is necessary, one can use external means like choppers and external modulators to do that. Then we have the all-important noise consideration. So let's divide that into two categories: short-term noise and long-term stability. So the short-term noise for this source is primarily dominated by the noise in the laser. So noisy laser will give you noisy source. In case of long-term stability, this is primarily affected by environmental conditions. So this source thermodynamically interacts with its environment. Pressure, temperature, density inside will be affected by the pressure, temperature, density outside. So let's now look at some factors that affect the noise stability and background light. There are many of them, so many that perhaps theoretical characterization may be difficult, but one can characterize empirically. So again, we have our plasma region. So G is pointing down, as we said. Laser comes from the bottom, and it's focused here. So what goes on? So remember, this is very hot, hotter than outside gas, and so there will be a tendency for a convection. So the gas will tend to rise, but at least once it rises, it will lose its ionization state because there is no laser light of density high enough to maintain the plasma. If you have any type of gas movement, you are going to have acoustic waves which can then bounce around the inner bulk. There will be diffusion. Hotter gas will want to diffuse into cooler gas. If there are density changes, then there will be refraction. So there will be refractive effects. Since there is a gas outside, there will be scattering effects. So light will scatter. So refraction and scattering are going to give rise to some background light. Finally, because we have a plasma of lower density than the surrounding gas and different temperatures, you have Rayleigh-Taylor instability, which will tend to create kind of waves or undulation in the boundary between the plasma and the surrounding gas. So this looks, from physics point of view, almost overwhelming. A lot is happening. And so this is when one goes to a lab and characterizes the source. And so what you see on this plot is a center of mass, or one should really say center of emission of light from the plasma region in the vertical direction and the horizontal direction. So this plot tells you by how much the center of emission is moving. And we see that the movement is on the order of a fraction of a micrometer. So this corresponds to spatial stability of the source. The source is not, the center is not fixed exactly at zero. That would be ideally, but the fluctuations from that zero mark are small. And here we see a setup that measures short-term power fluctuations. The light from the laser-driven light source is fed into integrating sphere where we control the brightness with the photodetector. And thus we see that the fluctuation of the radiant flux is on the order of, well, about less than 1% on all time scales and different powers of the laser. Here we see an empirical plot that shows relative output as a function of time. And the time here is in hundreds, in fact, in thousands of hours. And so we see that the typical decline of 10% in the output occurs in about 10,000 hours or so. So, as we said earlier, one great advantage of the source is its point-like nature. So because this is a point-like source, collimation and feeding of light into subsequent optical components like fibers is much more efficient. So light from a point source can be collimated with lenses, transported some other location, and then focused again and fed into a pinhole or a fiber. Please note that if the source is extended, then collimation is impossible. One could still collimate the light using a pinhole here. However, that would be very, very inefficient. You would only utilize a tiny fraction of light from the source. So this brings me back to a Blackbody source we discussed earlier in the presentation. To collimate the light, I would have to use the pinhole. If I want more light, I would have to make the object larger or hotter. So making the object larger makes poor collimation even worse. So when one thinks about this, one now sees the advantage of this point-like nature of our source. So some major takeaways before we go to the section discussing some applications. So high brightness, very small emission volume, broad emission spectrum from UV to IR, stable light output. Again, that is affected on the short time scale only by fluctuations in the laser, and relative to other sources, long lifetime. So let's look at increasing brightness. So we are here, and by the way, this is how the EQ, the laser-driven light source manufactured by Energetic, looks like. So it's a box. Inside of the box is the bulb with the gas, and light comes in from laser by fiber and comes out by a fiber. So we see that on the increasing scale of brightness, only super continuum source can provide higher brightness. But let's remember that these sources do not produce much of UV light, which some applications may utilize. So some table to ponder. So this is a table with some competitive analysis. Let's start with the spot size expressed in millimeters. And so our source, the laser-driven light source, has indeed the smallest spot size compared to the lamps or the tungsten halogen Blackbody source. Output stability is pretty good, and it's not the best, but it's also not the worst. Another competitive advantage is the very long lifetime compared to the other sources. And of course, the top row shows the relative pricing. This is a larger table, again, for you to ponder during the weekend. So this lists some of the properties of the laser-driven light source as compared to other sources that we discussed, like arc lamps, LEDs, lasers, or superluminous diode, etc. So perhaps I'll just mention one important one, because there's usually some questions about that. The laser-driven light source do have indeed a rather longish warm-up time. So when you turn on the system, the light is not produced instantaneously. It takes time for thermodynamic conditions to equilibrate. This is in contrast to, for example, lasers, where the warm-up time is extremely short. Another advantage of lasers, of course, is that you can modulate them or create pulses of incredibly short duration. So in the last few minutes that we have, let's discuss some possible and existing applications of LDLS sources. So let's begin with some key features again, and what benefits these features produce. So we have high radiance and small emitting volume. So that creates high throughput for microscale illumination. So we have high spatial stability, and that produces lower light output noise. So remember, for lamps, we had flickering. So here, there is no issue with flickering because there is no rusting of the electrodes, or certainly not to the extent that you get in the lamps. And also there is no spattering, since plasma is not in contact with the electrons. We have a very stable source that allows basically day-long 24/7 operation, and that will eliminate frequent system recalibrations. So if you did not have stability, if the light changes, then one has to recalibrate the system. And very long lifetime of the bulb, 10,000 hours or more, which leads to lower maintenance costs and avoidance of downtime. So LDLS sources can be used in a variety of applications. Here are some like sensor calibration, metrology, spectroscopy, microscopy, and imaging, and more. Here is another table to ponder about. So in the left column, we have some applications, well-known applications. In the second column, you have a current technology. In the next few columns, you have various attributes and requirements of the applications. And in the last column, you have a discussion, short discussion, whether LDLS source is competitive, whether it's possible to use or not. So for some applications, the answer is yes, competitive and possible. And for others, perhaps not likely, like for the first one. So let me discuss the first application, which is actually a product that Energetic makes, and this is known as Chromatic spectral engine. So this is a product that can generate spectrum, desired spectrum. It uses LDLS source. The basic idea is as follows. We take light from the LDLS and produce a spectrum projected on controlled mirrors, electronically controlled mirrors. The mirrors are either in on or off position. And by reflection from mirrors that are in on position, I can collect light in the collecting fibers and thus have light of a desired spectrum. So the mirrors can control both spectral wavelength and also an amplitude, because I have a number of rows of these micro mirrors. So here we have a little rainbow spectrum projected onto the mirrors. And again, by switching them on and off and feeding the light into collecting optics, I can generate a desired spectrum. So the way it works, you specify the spectrum that you want. Like in this plot, the yellow line shows the target spectrum, and the instrument, the engine, spectral engine, is going to generate the match. And as this plot indicates, the match is quite good. There are a variety of issues here. Let me just say one thing, that not every spectrum can be generated. There are some constraints, but if the spectrum is not something unusual or difficult, the match or generation is quite good. So using LDLS source and the spectral generator, one can use the system to, for example, perform calibration of detectors. For example, we have an array of CCDs or photodiodes, which I would like to calibrate or test, maybe test their quantum efficiency or some other aspects. So the light then would go into basically a spreader, homogenizer, which spreads the light uniformly onto the detectors. Another interesting application is spectroscopic ellipsometry. This is the technique where you illuminate a sample whose properties you would like to study, like, for example, thickness, the critical dimensions, composition, or other aspects. You vary the polarization and wavelength, and you detect the reflected light with analyzer. One can then compare the results, the data, to the models of the sample. Another interesting application is spectroscopy, where the light from our source is allowed to propagate through a column of gas, whose composition I would like to determine, study, and thus produce the spectrum, broadband spectrum, which then indicates the presence or absence of gases in question. The advantage of the source is that because it's bright, it will produce a high signal to noise ratio, which means that you can detect small or trace amounts of gases. We have high spatial and temporal stability, which allows the high speed and long lifetime. Another interesting application of the source is flat fielding. So in any professional astronomy, before or after observations, one needs to perform a flat field. So what happens is one illuminates the telescope with either dome flats, so this is a flat and bright surface, or one can look at the blank part of the sky. Usually it's done before sunrise or shortly after sunset. These will be known as sky floods. However, getting sky floods may sometimes be very difficult or impossible in the heat of the moment. And so dome floods is what one would rely on in those cases. So this has to be done for any professional astronomy to calibrate the CCDs. You could also calibrate spectroscopic devices using the spectral engine. And the final example of application is ultraviolet hyperspectral microscopy. So hyperspectral imaging is one where you obtain both an image, visual image of the sample, but also the spectrum per element or resolved element. So if I am going to use a CCD, so CCD is going to give me an image, but for every pixel in the CCD, I'm going to get the spectrum. Thus, you obtain both imaging and spectral information about the sample. Since the sample is microscopic, we would like to use light of short wavelength because that gives me a higher resolution. And so here you see the great advantage of the EQ source. It has high brightness and also UV light, which, for example, Super Continuum does not provide. So some takeaways from this section. So LDLS superior features are high brightness, broadband, stable output, long lifetime. And application fields, again, semiconductor, metrology, photonics sensor calibration, colorimetry, spectroscopy, hyperspectral imaging, and possibly more. So I'd like to thank everyone for listening to this webinar. Again, my name is Slavomir Piatek. If you have any questions about this webinar or technical aspects of the source, please contact either me or Bill Grub. Bill, especially if you have technical questions about the sources themselves. So again, thank you very much. And until next time, thank you.
Great, thank you very much. We have a few more minutes left of our webinar to answer some questions. We don't have any questions in the Q&A box right now, but there were some that were put into the chat. And so I will go ahead and read through some of those with the spare time that we have. Okay, so from Nanu, is it possible to modulate the LDLS output for a specific application?
Right, so the modulation, so I'll try to answer this question, but Bill may add to it. So modulation is actually difficult because to modulate the light output, you have to modulate the laser. That's easy. However, when you modulate a plasma region, its thermodynamic properties change. So the spectrum is going to change, the size is going to change. So some modulation is possible, but there are practical limits.
Okay, great, thank you. Another one from Joseph is, from a cold start, how long does it take to reach a stable light output?
So from my recent experience, it took more than about 15 minutes. 15. So it's not seconds. It's not even single minutes. It takes some time. Yeah.
Okay. Another one from Vataly is, you mentioned approximately 1 micron spot size for the LDLS, and they were curious about what that really meant.
No, it was by spot size, we meant the size of the light emitting region. So that would be few tens by few tens microns in case of the source. So so the plasma has a volume, right? If you look at that volume, kind of, you know, looks like an area. So that would be the spot size.
Great, thank you.
Okay. So I would like to point out that spot size is still quite small, one of the smallest for other similarly functioning light sources like discharge tubes.
Great, thank you. Another one from Joseph earlier in the session was, does the laser excited plasma require continuous voltage at the electrodes for stability, or can the voltage be removed?
Right, so the voltage is removed. Of course, the laser can be on, that doesn't hurt anything. The voltage only ignites the plasma. So the laser cannot ignite the plasma, right? You have to have voltage stimulation. Once you ignite, once you start the plasma, the voltage is removed. And so therefore, the plasma arc no longer extends from electrode to the electrode, but it's only, or its volume is dictated or determined by the region where photon density from the laser is high enough to maintain that plasma. So remember, the inverse Bremsstrahlung depends on photon electron interaction, but you have to have enough of those photons, these are again from laser. So only in a small volume, this condition will be satisfied. If it's not, then the plasma will simply neutralize.
Okay.
But that, I should point out, is actually very great advantage of the source. The small size is the advantage. And the advantage, as we said, for the light collection, but also you do not corrode the electrodes. So there is a very limited amount of corrosion and sputtering. So the glass lump is not going to darken as fast as, for example, the arc source, the ordinary arc source.
Okay, great. We have another one from Nander. Can the LDLS be used in it as a field calibration source, or is it just for lab use?
So maybe this question I'll ask Bill to answer. Bill, if you are there, could you answer this question?
I'm sorry, I was typing answers in the chat here. So could you repeat the question?
So the question is, can LDLS source be used in a field? So is it only meant to be a lab benchtop device, or can it be used in a field?
To be honest, it's really designed for indoor use. If we were to use it in the field, we would need to just maintain the environment, the operating temperature, and so forth. But that is possible. But it really was not designed to be used out in the open.
Okay, great, thank you.
Having said that, it's not requiring a clean room or anything like that. Just typical laboratory environment.
All right, I think we have time for about one more question here. One that popped into the chat from Khan is, why 974 or 1070 nanometer lasers? Is it possible to use another wavelength that says a visible or mid, far IR? What is the difference between the different wavelengths? Maybe
again, I'll ask Bill to answer this question.
Yeah, so the IR wavelength that Slawomir mentioned is used in part due to the absorption properties of the xenon gas, and it has been proven over the years with our products to be effective. So I'm sure you could potentially use other wavelengths, but this is the one that, or at least the region that he described in wavelength, is the region that we have found successful.
Okay, great, thank you. Unfortunately, this is all the time we have for today. Again, I'd like to thank everyone for joining us today and for Slawomir's great presentation. A recording of this session will be sent out via email in a few days, so please watch for the post-event email if you are interested in reviewing today's sessions. If your questions did not get answered today, you may reach out to me directly at emilyb@spie.org or to one of our speakers today, Bill or Slawomir. To see a completed list of webinars for our community, please go to spie.org/online. And Hamamatsu will be putting on 3 more webinars this year in the coming months. So please refer to the SPIE online calendar for updates on when those will be happening. Great. Thank you very much, everyone. Enjoy the rest of your day.
Thank you. Thank you. Bye.